So here we are going to study about the concept called to be equipotential surfaces. What do you mean by this equipotential surface? The name itself is self-explanatory. The surface on which the potentials are considered to be what? The surface on which the potentials are considered to be same or equal at all points. Then the surfaces are called to be equipotential surfaces. So it can be defined like this. Any surface which has the same potential at each and every point is called to be equipotential surface. We can consider the equipotential surface in some other way also. In other words, we can say that the potential difference between 2 points on the equipotential surface is zero, because on a surface at all points we are having the same potential. So let us consider this point as A and this point as B. So potential at A is VA and potential at B is VB. Both are equal on this surface. So difference is what? VB difference VA, which is equal to, since both are equal, the difference in potential on that surface is equal to zero. This is the second definition. So in order to explain the properties, let us consider an equipotential surface. So in order to consider an equipotential surface, I have taken two examples. One of the example, I have taken a point chart. See, in case of a point chart like this plus Q, the electrical lines of forces are acting radially outwards. Now, if you want to calculate or if you want to consider an equipotential surface at a particular distance R or R1, take the charge as center and R1 as the radius. You just drop a circle or a sphere, you can able to get a surface which is equipotential. And on the surface, you can able to get the potentials are same. Similarly, if you are considering the equipotential surface at some other distance, you can able to get another equipotential surface like this. So I can write, in case of a point charge or for a point charge, the equipotential surfaces are in the form of concentric spheres. Okay, then the next line. The next example, let us consider an uniform electric field. Usually, an uniform electrical field is represented by drawing parallel lines. Let us consider that uniform electrical field represented as E. In this, how the equipotential surfaces will be? The equipotential surfaces will be perpendicular to these electrical lines. And if you are considering more number of equipotential surfaces, the surfaces are parallel to each other. So in case of an uniform electrical field, the equipotential surfaces will be parallel planes, and that equipotential surfaces are perpendicular to that electrical lines of force. So you consider both the cases, that is in case of the point charge and in case of uniform electric field. In general, we can write the equipotential surfaces are always perpendicular to the electrical field lines. We can take this as one of the property of electrical equipotential surfaces. So equipotential surfaces are considered to be perpendicular to electrical field lines. We can write the difference between the 2 points on an equipotential surface. Let us consider one point as A and another point as B. So the difference in potential is VB minus VA, which can be written as dV. This dV can be written as minus of E into dl. That is, we can get a relationship between potential difference and electrical field, that we can see in the next part of this equipotential surface. First of all, you just consider this alone. How we can able to get this relation, I will be deriving it in the next part. Then what is the second property? See, if you are moving a charge from one point to another point on an equipotential surface, we are in need of a work. That work done is equal to zero. Why? If you are moving a charge Q or Q0 from point A to B, it is represented as the work done from the point A to point B is equal to the charge moved Q into difference in potential. See, difference in potential on an equipotential surface is equal to 0 because both VA and VB are equal. Therefore, work done is equal to 0. So what is the conclusion then? Conclusion is the work done in moving a charge or an unit positive charge between any 2 points on the equipotential surface is equal to what? Is equipotential surface is equal to 0. This is the second property. That is work done in moving a charge from one point to another point on an equipotential surface is 0. Then what is the third one? The third one is the spacing between the equipotential surfaces enables us to identify the regions of strong and weak fields. That is, when you are considering the electrical field E and the distance, electrical field is inversely proportional to that of the square of the distance for a point charge. In general, we are with the relation between potential difference and electrical field, we will be having E is equal to minus of dV by dr. This relation we have to derive. Let us derive how we got this relation. Let us see it later. But in general, we can say electrical field is inversely proportional to distance. So as the distance decreases, electrical field increases. So if the equipotential surfaces are closer together, then electrical field is higher and vice versa. Based on this, the third property is given. That is the spacing between the equipotential surface, whether the equipotential surfaces are closer or far apart, enables us to identify the regions of strong electrical field and weak electrical field. This is what we are calling it out as the properties of equipotential surfaces. See, we are going to get the relation between the electrical field intensity and potential difference. In order to study the relation between electrical field and potential difference in air medium or in free space, consider a point charge plus Q placed at O. So around that, you will be producing or developing an electrical field E. In that electrical field, along the line of the charge, you consider two more points, A and B, separated by a small distance considered to be dr. Now, you consider an unit positive charge at A. Let that unit positive charge is represented as +1 coulomb. Now, I have to move this unit positive charge from A to B. For moving this unit positive charge from A to B, I have to do a work against the electrical field. Since A and B are very close to each other, or the distance is taken to be very small in between them, the electrical field between A and B is taken to be constant. Now, I have to calculate the work done in taking the unit positive charge from A to B. So, I have written it here. The work done from A to B equal to, initially the work done is given by force into distance, F vector dot dr vector. See, instead of F, I am writing it as E into dr because the electrical field is represented as force per unit charge. So E is equal to F. So I am replacing F with E. So I am getting E into dr. Take it as equation number 1. See, if I am considering work done from A to B, according to the definition of potential difference, the work done in moving an unit positive charge from A to B against electrical field is nothing but potential difference dV. So potential difference dV is equal to final potential minus initial potential, that is VB minus VA. Now you consider this equation number 3. For equation number 1, instead of writing work done as E into dr, I have written it as minus of E into dr because the negative sign indicates that the work done is against the electrical force or against electrical field. So in order to represent the work is said to be done against the electrical field, I have represented the work done with one minus. So work done from A to B is minus of E into dr. Now equate this equation 3 and equation 2. Since both the left hand sides are equal, I can equate both the right hand sides. So if I am equating the right hand sides, I can write like this. dV is equal to minus of E into dr. Rearranging this, I can get dV is equal to minus of E into dr or E equal to minus of dV by dr. This term we are calling it as the relation between electric field intensity and the potential difference. So in this relation, potential is divided by distance. Any quantity divided by distance is usually represented as gradient. Here potential divided by distance, so it is called to be potential gradient. But that potential gradient is having a negative sign. So we can say the right hand side as negative gradient of potential or negative potential gradient. On the left hand side, we are having electrical field. So we can get the definition for electrical field as electrical field is equal to negative potential gradient. We can state another unit for electrical field with this formula. Potential measured in terms of voltage, distance measured in terms of meter. So electrical field represented as volt per meter is another unit for electrical field.